Several years ago, I had an undergraduate student in the lab, Allison Pouch, and Allison was doing mathematical modeling for acoustic wave backscattering from a sphere. Once she got her code running and had verified that it matched the well-established results in the literature, she was very excited to come tell me that while her MATLAB code ran instantly on just a run-of-the-mill desktop, in 1960, those same results required the use of 2 computers for 2 months. And I said, oh no. Go read the acknowledgments to that paper where Professor Anderson thanks by name those 2 hardworking computers. In 1960, computer was a job title, not a machine. I'm Professor Mark Hinders, Applied Science Department at William & Mary. So the modeling that we were doing was in support of one of our former PhD students, Ted Lynch, who was commercializing an FDA-approved device to use during heart surgery called EDACS. It detects, tracks, counts, and sizes emboli in the bloodstream. The idea is that some fraction of people who have heart surgery come out of it with cognitive deficit. Sometimes that cognitive deficit is temporary, sometimes it's permanent. And what happens sometimes is when they're hooked up to the heart bypass circuit, some air bubbles get entrained in there, and those air bubbles, if they're not filtered out somehow, can make their way to the brain and eventually plug a vessel that will stop the flow of blood, and then distal to that, the brain will be starved of oxygen, and that's where the damage comes from. And so this device existed using ultrasound backscatter to detect, track, count, and size bubbles in the bloodstream. And what we did was the high-level mathematical modeling of that physical interaction of the acoustic wave backscattering from the air bubble in the blood in order to help refine the algorithms for the sizing of the bubbles. So that's what Allison was working on. And it worked really well. The outcome of that was simple rules of thumb that could be implemented on the existing FPGA processing power in the device in order to refine the ability of it to size the bubbles. One of the issues with devices like this, you are in effect saying to the heart surgeon, look, we need to add this device to your procedures so that your patients don't get brain damage. And almost all of the surgeons will say, well, of course, my patients never get brain damage. It's those other surgeons whose patients have problems. I don't really need this device. And so it does happen. Getting rid of the bubbles in the blood is something that you would like to have happen if you or a loved one is having this kind of surgery. And so inside the heart bypass circuit is a reservoir, and the blood comes in the top, comes out the bottom. The idea then is buoyancy can help debubble the blood somewhat. So the next thing that we did with TED as sort of an improvement to their device was do modeling for the radiation force from a transducer going up from the bottom of that blood reservoir to the top to give the bubbles a bit of a boost to better debubble the blood. And the idea is the scattering analysis allows us to size the bubbles, and then we could, in principle, then tune the frequency of excitation of the radiation force transducer to optimally debubble the blood. And then part of the sales pitch to the clinicians is adding this technology to your existing system will allow you to have a smaller reservoir for debubbling, and that will reduce the amount of blood that you need to transfuse in heart surgery, which uses quite a lot of blood. So the next part of the project was not just calculating the scattering of the ultrasound from the bubbles, but instead now calculating the radiation force. So radiation force is a complicated physical phenomenon. Mathematically, it's the backscattering we can do with linear analysis, but radiation force, you're going to have to include nonlinear analysis. So that makes the equations much more complicated. The other issue that we face both in the scattering analysis and now the radiation force analysis is the value of viscosity that's going to be used. So blood is thin to various amounts in this process. And one of the questions was how much does the blood thinning affect things? Does it affect the EDACS part of it, the bubble tracking? And that's a fairly straightforward thing for us to do in the mathematical modeling. We included viscosity in our analysis. There's a couple of different ways to do that. There's some judgment around how complicated you want to make that be. And so, but we implemented those equations, had viscosity as a parameter that we could tune, and we found for the backscattering part of it, viscosity didn't affect the results very much, and that simplified the implementation of the algorithms in the device. For the radiation force analysis, we had every expectation that viscosity was going to matter. So the first thing that we did was we looked in the literature to see what was known, and we found papers from, say, the 1930s that talked about this, and papers up in the 1990s and later. And what we found is that there was a range of complexity to the models that we could use for this analysis. And we settled on two separate ones. One, the Hasegawa model, did not include viscosity at all. And so we implemented that model, and we found that our results match perfectly for those fairly standard results. And then there was another model, a Russian model. Dornikov is one of the primary authors. We read those papers and implemented those results. And one of the strange things about the Dornikov papers, sort of stereotypical Russian mathematician, if you wish, had lots and lots of equations, long papers, but almost never showed us any results. And we spent, this was Kara Leckie was doing this, PhD student, and Kara spent quite a long time implementing and verifying the consistency of the Dornikov results. And one of the things that she found is that presumably the reason Dornikov didn't show any plots in any of his papers is that he didn't have a big enough computer, because the simple thing of adding viscosity to the analysis meant that the equations were complicated enough that it required a supercomputer to implement them. And we have a Beowulf-like, something we call Cyclone. It's a parallel cluster that we were able to use for this sort of thing. Okay? So we implemented the inviscid Hasegawa solution, the viscous Dornikov solution, and one of the issues with these complicated models is once we get the programs running and we're ready to show results, we need the input parameters. And one of the little frustrating things about this analysis was going back to the clinicians and asking them, okay, we need the properties for the blood at various temperatures, we need speed of sound, we need density, we need viscosity, right? And over and over and over again, the answer would come back, well, we don't really know what those material properties are. Fortunately, I happen to have an old copy of comprehensive compilation of acoustic properties of mammalian tissues at ultrasound frequency, something like that, and was able to get an estimate of what the input material properties were for the model. Even when the clinicians couldn't quite tell us what they were, they could sometimes say, well, it's like this tissue or it's like that tissue, and we could get an estimate of what the material properties needed to be for input to the model, and also what the range of them were. And the punchline to the story is we built this god-awful complicated model that we implemented on a supercomputer, and then when we ran the model for radiation force, accounting for uncertainty in the input parameters, we found that the inviscid model gave the same prediction within those uncertainties. And so In some sense, that was good. That meant that to use this mathematical modeling of the radiation force physics, we didn't have to use the too complicated model. We instead could use the simpler one that gave the same results within the uncertainty of the input parameters. So then we have this complicated model for nonlinear acoustic radiation force scattering from a sphere. And we were wondering what else you could use that for. And just at that time, William and Mary was involved in a large project that was designed to use wild algae to both clean up the Chesapeake Bay and make biofuels. So the idea is that each year the Chesapeake Bay agricultural runoff and whatnot causes algae to bloom, and then when the algae dies, it sinks to the bottom, and that takes up oxygen. So when the algae grows, it feeds on the agricultural runoff, the fertilizers and sewage runoff kinds of things. So it's good in some sense that the algae takes up those excess nutrients, but then if the algae is left to sink to the bottom and die, that can then kill the fish. All right, so the idea behind the algal turf scrubber is that you deliberately grow algae in big ponds, and then you use that. What the algae does is it cleans the water, and then periodically you harvest the algae. And the question for this research project was, could we make this work in terms of not just the environmental application, but could we make this a viable technique for making biofuels? And there's different kinds of algae. Some make one type of fuel, some make another type of fuel, some aren't good for any other type of fuel. And so one of the issues is how you separate out the different kinds of microalgae for different kinds of processing. And some are sort of think of oily sort of things, and in the embolus analysis we had done that both for air bubble embolisms and also for lipid embolisms, and those range of material properties. We had all of that. We had the range of viscosities we could put input to our radiation force model, and so Kara adapted her radiation force model with viscosity to use it as a tool to design systems to sort different kinds of microalgae using radiation force. So you can set up a standing wave cell with the water flowing through it, and then the radiation force will cause the individual algae to sort into the nodes or the antinodes, and that can be an efficient way to sort the algae, because the point is here, even in those days, oil was maybe close to $100 a gallon or $100 a barrel for a while. You still don't want to have it be too expensive. And so we adapted this mathematical model to radiation force for sorting microalgae, and we were a part of bidding on $200 million super consortia. We had a few $1 million of seed funding from a Norwegian oil company, and we're getting ready for a much larger project, $100 million-ish project that this would be sort of a small part of. And ultimately that large project never quite happened, putting together big consortia involving multiple universities and industry partners and all that is fairly complicated, and that deal never quite got done. We heard through the scuttlebutt, we heard that Department of Energy was a little disappointed that William and Mary's proposal never quite got to them. It could be that if they had gotten all the I's dotted and T's crossed in the grants office of the various institutions, that that very large research project 10 years ago or so would have ended up with and nonlinear acoustic radiation force-based system for sorting microalgae to make biofuels. I'm Professor Mark Hinders, Applied Science Department at William & Mary, as.wm.edu.